Hi everyone, in this video we are solving problem 1 of lesson 3. In this problem we have a magnetic circuit which is represented here, and we know that here we have a current, and in the central branch of this magnetic circuit we have 104 turns here in this coil, okay? And we also know that the magnetic flux in this right branch here is 10 up to -3 Webers. Relative permeability of the material is 400, cross-section 10 square centimeters, and length here, each of these lengths L are 10 centimeters, okay? So they ask the magnetic flux in this central branch. So first of all, this is the diagram which represents this magnetic circuit. So we are going to distinguish between the magnetic flux in the different branches. So here we are going to write that this magnetic flux in the right branch is going to be Phi1, and the magnetic flux in this branch is going to be Phi2. While here we have this magnetic flux here in the central branch, where we have the current here entering into the system, which produces an electromotive force, which is the product of the number of turns multiplied by the current. So if we come here to this node and we apply the first Kirchhoff's law, in the same way as we could apply the first Kirchhoff's law to currents, we can do the same with magnetic fluxes. So there you have this magnetic flux, and that must be the same as the sum of these other two magnetic fluxes. So the way in which we can apply the second Kirchhoff's law to that mesh is by doing the following thing. The electromotive force was the number of turns multiplied by the current, okay? So in this mesh, we have that the electromotive force must be equal to, here in this side, here we have a mesh, so in this branch we have phi multiplied by the reluctance of this path here, which is the central branch, so phi multiplied by the reluctance, okay, plus in this other branch we have Phi2 multiplied by the reluctance of this magnetic length here, reluctance 2. If we do the same with the right branch, the electromotive force is going to be the product of, here you have Phi multiplied by the reluctance, which is this side here, and in this branch you have Phi1 multiplied by the reluctance 1. So here you have three expressions, and in these equations you know the magnetic flux in the right branch, and you also know the number of turns. So what are the unknowns in this expression? Well, the unknowns are going to be the magnetic flux in the central branch and the magnetic flux in the left branch, and also the current. The reluctances, you can obtain them because they depend only on geometrical magnitudes and on the permeability of the material that we are considering. So as here you have three equations and three unknowns, there are several ways in which you can solve for the component that they are asking. But I'm going to do the following. As you can see here in the term in the left, you have the electromotive force, the product of the number of turns and the current. And here in the other side, you have this. So then, we can write the following. If this and this are the same, this side and this side, they must be the same. So you have this equal to this. So there, you get up to this. Okay? Reluctance here in the left branch, 2 divided by L, permeability, and here this, okay? This was the reluctance in this side. And the reluctance in this other side is 3 times the length, and here the permeability and the cross section. There, you need to obtain a common denominator. You will have 5L divided by 2 times the permeability and the cross section, and the magnetic flux here in the left branch, and in the other side, on the other side, 3L permeability cross section magnetic flux 1. So here in this expression we get to the following time: 2.5 times phi2 it's equal to 3 times phi1. Okay, so that means that phi2 is going to be the same as 6 divided by 5 times phi1, which is 1.2 times phi1, as phi1 was 10 up to minus 3 Webers, so there you have 1.2, 10 multiplied by 10 up to minus 3 Webers. So this is the magnetic flux in the left branch. So now that you have the magnetic flux in the left branch and in the right branch, if you go here to the first equation, you need to do this plus this gives 2.2 multiplied by 10 up to minus 3 Webers. So now we have the first thing that they asked, which was the magnetic flux in the center branch. So what else do they ask? They ask the current flowing here. So then you need to use one of these expressions. Let's calculate the reluctances. So the reluctance in the center branch will be the length of that branch divided by the permeability and the cross section. So the length in this branch is L, that's 0.1 meters. And here in the denominator we have, this is the relative permeability multiplied by the permeability of the vacuum, and the cross section you have to change to the square meters, okay? So if you do so, the reluctance that you obtain in the center branch is approximately this one, in hundreds up to minus 1. So if you do now, for example, the right branch, its reluctance will be reluctance 1, and here in this side you have L plus L plus L, okay? This is the right branch. This is the length of the magnetic path in the right branch. So there you have 3 multiplied by this length. There, the material is the same, so same permeability. And the cross section is S. So you change the units to the square meters, and you get this value for the reluctance. If now you do the left branch, you will have reluctance 2. So here, as you can see, you have in this length and this length, the cross section is S, okay? So you have that. And in this other length here, the cross section is 2S. So we are going to separate these two terms in the expression of the reluctance. So there you have 2 times the length divided by the cross section and the permeability, plus, that would be this path in blue, plus the length divided by the permeability and 2 times the cross section. You can introduce the values and you are going to obtain this result for the reluctance of the left branch. So if you use, for example, this equation, here you have the 3 reluctances that we have obtained, so you only need to introduce the values in this expression, and then when you introduce the values of the reluctances of the central branch and the reluctance of the right branch, then you can get the value of the current, which is 9.945 amps.